In this set of slides, we're going to look at the accumulator and we'll review the calculations that we need to do to ensure that the bottles that we have in our accumulator are sufficient to operate the RAMs that we have in our BOP stack according to the law. Here's the configuration of a typical accumulator, also known as a Kumi unit. We can see the bottles, which in the accumulator that we'll have for our exercise, the one that's at the PERT lab, we've got 10 bottles that have an effective volume of 10 gallons each. We've got a reservoir tank and then the BOP stack. When we charge up the bottles, we'll take fluid from the reservoir tank and put that into the bottles. When we function the accumulator to open or close the rams, the fluid will leave the bottle and it'll come back to the reservoir tank. As long as we've got the electrical pump or the air pump, we'll continually fill the bottles up every time we make an action. What we're going to review today is what we'll do if we lost air simultaneously when we lost the electrical pump. This will only let us use the stored energy that's in the bottle while we have no energy to replace the fluid that we use from these bottles in the accumulator. Here's a cross-section of a typical RAM preventer. This RAM block could be a blind RAM, a pipe RAM, or a variable bore RAM, similar to what we have at the PERT lab. Here you can see the ram shaft and the piston. To the left of the piston is the opening chamber. To the right of the piston is the closing chamber. Here you can see how the closing chamber and the opening chamber are aligned together. The closing ratio is equal to the piston area divided by the ram shaft area. The minimum hydraulic fluid pressure to close against the surface pressure is the surface pressure divided by the closing ratio. This could dictate for us the minimum pressure above, if depending on our surface pressure, what law states is 200 over the pre-charge pressure. Here we have an excerpt of the Bessie regulations in regard to the accumulator. Importantly, it says the accumulator system must have sufficient capacity to supply 1.5 times the volume to open and close all the equipment with a minimum of 200 pounds above the pre-charge pressure. Here we'll start looking at the volume calculations. The bottles that we have, they're 11 gallons, and the bladder inside the bottle is 1.0 gallons. That leaves us an effective 10 gallons. So when the bottle is pre-charged solely with nitrogen, the nitrogen volume is 10 gallons. Now when we charge up the bottle to 3,000 pounds, we're going to have much less nitrogen because we'll smush this nitrogen in the bladder by this hydraulic fluid that we pump in. This bladder is essentially acting like a spring. This is to give us this push to get the fluid back. So we'll take 1,000, which is our pre-charge, plus 14.7 rounded off to 15, that's the atmosphere, divided by 3,000 plus 14.7. That gives us 3.36 gallons of nitrogen. Now to get gallons of hydraulic fluid, we'll take the 10 gallons, which is the size of the bottle, minus this 3.36 gallons of nitrogen. That'll give us 6.64 gallons of hydraulic fluid. So now that we know there's 6.64 gallons of hydraulic fluid, we want to know how much of that is usable. Bessie regulations tell us the accumulator pressure must stay 200 psi above the pre-charge pressure. So we take the nitrogen volume of 10 gallons times 1,000 plus 14.7 divided by 1,200 plus 14.7. That gives us 8.35 gallons of nitrogen volume. So we subtract 10 gallons minus the 8.35 gallons of nitrogen, and we're left with 1.65 gallons of hydraulic fluid. This is 1.65 gallons of hydraulic fluid that by law we're not allowed to plan to use. However, in an emergency situation, if you reach 1200 psi and you had some kind of an emergency, you would still function the ram. This 200 pounds is really a safety factor. So 6.64 to minus 1.65 gives us 4.99 gallons of usable fluid. Here we see a table that gives us, based on the type of ram and its size and its working pressure, the number of gallons to open and close that ram or that valve. So an example, a rig is equipped with a 5,000 pound BOP that's got 3 10-inch Cameron blowout preventers, 1 high drill, 1 accumulator. The accumulator's pre-charged 1,000. The accumulator's working pressure is 3,000. So the Cameron Type F hydraulic valves would be the valve on the choke line, the HCR, and the valve on the kill line. So we'll come to the table and we'll read those values. So the Cameron 5,000 pound working pressure, 10-inch, it's got these open and close volumes, so this is in gallons. So we'll have to add those two together and multiply by 3. Then here the high drill, and then 2 of the valves, the HCR and the one on the kill line. So when we add those together, we get 34.4 gallons to operate all the equipment. Now, based on Bessey's regulation, we have to multiply this by 1.5. So here we get 34.4 times 1.5 is 51.6 gallons. So if we had a pre-charge of 1,000 and a working pressure of 3,000, that gives us basically 5 gallons per bottle. We would need 11 bottles.